What was that which we were dealing? Hyperconjugation. Yeah. Talking about hyperconjugated structures, right? Okay, hyperconjugated structures. We were talking about the hyperconjugated structures. That is stability of the, let me see, hyperconjugative effect and the stability of your radicals, right? You're talking about the hyperconjugative effect on the stability of the radicals. Now, what is the order of stability when we consider the hyperconjugative effect? Now, inductive, we have considered the stability of, free radicals based on two facts. One, inductive effect. I'm just reminding you what we have talked last time. See, by inductive effect, I have this radical and this radical CH2 dot and CH3. Now this radical and this radical, the inductive effect will increase the electron density on this. It will increase electron density. H. And these two hydrogen also. H. And H. These two hydrogen also will increase electron density on this carbon. But here, this one, you have only 3 hydrogen atoms. 3 hydrogen atoms, H and H. Only 3 hydrogen atoms, and that also will increase electron density. So as you increase the number of, now this in turn will flow the electron to this side. This is all by inductive effect. Okay. Now as you increase the number of hydrogens and number of methyl groups, as you increase the number of hydrogen and number of methyl groups, what happens? The electron density on this carbon increases. That means there is concentration of electrons. Concentration of electrons on the carbon. And therefore, decrease of stability. Decrease of stability. Now we have explained hyperconjugated effect last time, and we have understood if you have CH3, I'll put the CH3 here. If you have this simple CH3, H, and H here, you have a dot, a radical. Now see what is hyperconjugate effect. Any hyperconjugate effect of this? No, nothing. No hyperconjugation. Remember, this cannot go here. Not possible. Please write this down in your book. See, this is not possible. See, this breakage of electron is not allowed. Why? Because they are mutually perpendicular orbitals. We have completely discussed this last time. But in this case, see here. When you have an alpha hydrogen, here is a radical. These two hydrogen will not participate, but the next hydrogen on the next carbon will participate. See here. You can see a double bond formation here. And this H become a radical. See the result of this. H, C, H dot, C double bond, C, H, H. See this. Okay. So what is happening? The lone pair of the odd electron is moving towards towards a hydrogen atom, right? So all of them can participate. You have one more hydrogen here. All these hydrogen can participate. That means there will be three equivalents of hyperconjugative effect because of one methyl group. So there will be four structures. There will be four structures. One using this hydrogen, second using this hydrogen, third using this hydrogen. Suppose I replace this hydrogen also with a CH3 group. See here. H, 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 C, H, C, H, H, and H. See, if I replace one more hydrogen with a CH3, that is secondary free radical. Secondary free radical. What is the consequence? You have 6 participating hydrogens. 1, 2, 3, 4, 5, and 6. And this original structure. So you can write 7 hyperconjugative structures. 7 hyperconjugative structures. And that also delocalization. The negative, the odd electron is moving over to this hydrogen, this hydrogen, this hydrogen, this hydrogen, this hydrogen, and this hydrogen. So the odd electron is getting spread. It is getting spread, and that will lead to 7 hyperconjugated structures. Now, when the electrons are getting spread, more stability. So the odd electron is getting spread. Odd electron is spread over to the hydrogen atoms. Hydrogen atoms. Okay. 3 indicates of 3 hydrogen indicates of 3H sorry, for E type, 6H for isopropyl. This is what is isopropyl. See here. This is isopropyl. Okay, isopropyl for 6H for isopropyl. And then how many H for T-butyl? 9H for T-butyl. So more the number of structures, more stabilization. More the number of hydrogens. More the number of hydrogens, alpha to the carbon bearing the radical. Alpha to the carbon with radical carbon. More stable it is. Right? Now see here, this is hyperconjugative effect. So, inductive effect destabilizes, hyperconjugative effect stabilizes. So, what is the net result? The one which is more powerful will win the race. Okay, so I'll write in the brief: inductive effect destabilize, destabilize. Hyperconjugative effect, write down all these things in your notebook. Hyperconjugative effect stabilizes. Right? So who will win the race? One which is stronger. One which is stronger. In this will win the race. Or okay. Now hyperconjugative effect. Hyperconjugative effect is stronger than the inductive effect. And hence tertiary butyl carbocation, free radical, TBU free radical. TBU free radical is stable than isopropyl free radical is stable than ethyl free radical. Again, in turn is stable than methyl free radical. Okay. Now think. So this is how you compare the stability of different species, and we have already discussed carbocation and carbanion. Okay, justify. This is a work for you. You have to do it. Justify the order of stability. The order of stability of A carbanion and B carbocation. Carbocation with proper drawings. And please remember, do maximum drawing, explain to in the drawing rather than writing full sentences. So please answer this question. I explained to you what is hyperconjugative effect and inductive effect and how they are stabilizing or destabilizing. Okay, so this is free radicals. Now, once we have, so what are things we have discussed so far? Very short form I have discussed. We have discussed the type of reaction that is bond fissions. This far we have come. Bond fission, homolytic and heterolytic. Okay, and then we have discussed about the electrophiles, and nucleophiles. Okay, erythrophils and nucleophiles. Then what did we discuss? Yeah, what was that? Uh, yeah, different reaction intermediates. Reaction intermediates. Uh, which include carbocation. Okay, then carbanion and the free radical. Okay, and their order of stability, their formation, everything we have discussed in detail. Okay, different types of carbocations like nitronium ion, sulfur trioxide, all these we have discussed in detail. Okay, then we have discussed in between, during the stability of these, we have discussed the inductive effect. Inductive effect. Then mesomeric effect or resonance effect. Did we do that? Mesomeric effect, did we discuss? Yes or no? One of you tell me. Have we discussed the mesomeric effect or resonance effect? It is also called resonance effect. Are you able to hear what I am talking? Yes or no? Can you hear? Rinchina? Are you able to hear? Or am I talking simply just like that? Can you hear?
Yes, yes.
Okay, okay. So did we discuss this mesomeric effect or resonance effect? Yes or no?
No, me.
That you have not discussed. No, then we didn't. Yeah, it's okay, good. So we have to discuss that now. So resonance is the effect of meso, and then we have discussed the hyperconjugation. Now we have discussed hyper. And once you write this answer, you will be more thorough with that. You have to answer that next time. Okay. So let us look at what is mesomeric effect. Right? We will discuss what is mesomeric effect. Mesomeric effect or resonance effect is very simple. You write resonance structures, right? Resonance structures is very easy to talk, but very difficult to practice. Okay. Let me draw the simplest resonance structure. We write resonance structures, resonance effect. I hope you people are writing on the paper, whatever I am writing on the board, or even whatever I am talking as the key points. I hope you are writing down. Now see here. This is benzene. Can you draw a resonance structure? Come on. All of you take your paper, book, and write the resonance structure of this. I'll give you 1 minute for that. Come on, do it fast. Draw the resonance structure. Yeah, simple to write, right? Here, 1, 2, and 3. Just move the electrons. Move the pi electrons, not the sigma electron. So that is the first thing you have to remember. So I shift these double bonds onto this side or this side. On either side, I shift the double bonds, right? So if I can reverse them back by writing like this. So there, So the actual structure is in between something, in between these two. That means the double bond character, for the double bond character is not concentrated on any between any two carbons. It is spread throughout. It is spread throughout. Okay, so that is resonance effect. Now you can write for different species. Say for example, you have a compound like this, a species like this, allyl radical, CH and CH2 plus. This is an allyl radical. Sorry, allyl carbocation. Okay. Now you have a positive charge here. Why does it get a positive? What is the geometry of this? See here. You have a carbon. You have a hydrogen here. You have a hydrogen here. You have a carbon here. And then you have yes, you have a hydrogen here. And see, you have two more hydrogen atoms. And there is, now see here, there is a pi bond between these two, and there is an empty orbital here. Okay, there's an empty orbital. Oh, this hydrogen I have drawn the wrong way. I'm not supposed to draw it like this. See, blender. It should be 120 angle. It should be like this. See here. Oh, okay. Now, C double bond C. Now you have included a p orbital here. That p orbital I will draw like this only, because it is perpendicular. Okay, and here also I can draw it like this. It's perpendicular. Right. Now suppose I turn the whole molecule out of plane by about 90 degree. The whole molecule I am turning by 90 degree. See what happens? The whole molecule along this axis, I am turning this molecule 90 degree. What happens? Draw the structure. This carbon, this hydrogen will come to the front. This hydrogen will go behind. This also will go behind. And this whole group will come to the front. So it will look like this here. So to H here. And now your p orbital will be like this. I hope you have understood the concept. And then we have hydrogen behind. See here. These hydrogen and this hydrogen are on the same side. And everything. Okay. Now this carbon, this bond is on the same side of this hydrogen. See, this hydrogen is, I will number the hydrogen, 1, 2, 3. So here is 1, here is 2, here is 3. Okay. Now, this group is on the side of this carbocationic group is on the side of H1. So let me put it in this way. See. And these two are in this plane. No, not like that. I have to rotate it so that they are towards, one is towards you, the other is away from you. One side. Where is my rubber? I have to release it. Yes. Now see, this also will come to the perpendicular plane like this. So, yeah. Now see. Now see here. This will come. One of them will. For another 10 minutes. We'll continue again. For 20 minutes more, please. Now see. So this is the status. Okay, this carbon is coming towards you, and one of these hydrogen will be one of these hydrogen will be backside, and the other will be front side. So here is the empty orbital. So this is the overall picture. Now you have 2 electrons here. These 2 are contributing, and here there is a bond formation. Now what can happen is, see here, these are parallel to each other. These orbitals are parallel to each other. And so what we can do is, we can shift this bond here. And what is the result? The positive charge here will be shifted to this. So you get the same result. This positive charge is shifted here, and the bond is formed between these 2. Okay? So there is a delocalization of positive charge. Okay? There is a delocalization of positive charge, and this I can represent like this here. And this is the double-headed arrow is the resonance effect, showing the resonance effect. So this is what is called resonance effect. So double-headed arrow means resonance. And you have to remember, resonance effect involves pi electrons. Resonance effect involves pi electron, not sigma bonds. You should never break a sigma bond. A single bond should not be broken. Okay? A single bond should not be broken during the resonance effect. Single bond means sigma bond. Single bond means sigma bond. Okay. Similarly, you can have another one, a vinyl chloride. Vinyl chloride. This also can stabilize. See here. We can delocalize these electrons. So this is stabilizing. So that forms CH2 minus. CH double bond Cl with a positive on the chlorine. Why does the chlorine get a positive? Because it is donated 2 electrons to form a bond. It has donated 2 electrons to form a bond. Right? Now here is another one. Very similar. CH2 double bond CH. CH. Single bond OCH3. Now this can shift here. That time what happens? This lone pair shifts here. Okay. So that will give you a resonance structure. What is that? CH3 minus CH2 minus then CH double bond oxygen with a CH3 and a positive charge. Why the positive charge? See here, you have removed these 2 electrons from here. Okay, so this is resonance effect. So the net result is the positive charge which was there on this carbon, the positive charge is delocalized over to this chlorine. See here, the positive charge is delocalized over this chlorine. Similarly, there is no positive charge, but it can, these two electrons can come to this CH2 group into an atomic orbital and form an anion, and there is spreading of charge. Okay, so this is basically what is resonance effect. You have to see H2 minus here with a pair of electrons here, lone pair of electrons. Okay, now let us write the resonance structure of aromatic compounds. That is more important than other ones. I'm giving you phenoxide anion. Here is phenoxide anion. Draw the resonance structures of phenoxide anion. The first structure I will write. Now the importance is one of them. You can see here, the lone pair is getting converted into a bond. That's the meaning of this arrow. The bond is getting converted into a lone pair. This bond is getting converted into a lone pair. That is the meaning of the second arrow. Okay. Write the result of that. Write down the result. All of you write in your book. Follow the arrow. Don't do anything else. Only just follow the arrow. Direction in which the arrow is moving. Where is the arrow ending? Yeah. Write within 1 minute. Yes. All of you write. Double-headed arrow should be shown to show the resonance effect. Okay, drawn. I hope you people are drawing. Otherwise, if I was in the class, I could have directly asked you people to come to the board and write it. But I don't think that will work here, unfortunately. Okay, now let me draw it. Look very carefully. Please learn this very clearly. Please try to do this. Now here is, see this. This lone pair of electron is used up. There is a negative charge here. Sorry. It's a phenoxide anion. Phenoxide ion. Phenoxide ion. Or phenoxide anion. Okay. Now look at that. You had 3 pair of electrons. Out of that, one lone pair has become a double bond. One lone pair has become a double bond. Okay, and now the charge has got neutralized. Now, so that is right. Now, what is the result of that? You get 5 bonds here. If I draw a double bond here, you will get 5 bonds here on this carbon. That cannot happen. So what we are doing? We are shifting these pair of electrons from this pi bond. From one of these bond is a pi bond. So take these pair of electrons over here.